Good morning, and thank you for joining today's webinar from Spec Innovations, Strategic Engineering Decisions with Innoslate. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping.
Yeah.
During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate Users Group or through X using the handle @Spec Innovations. We value your feedback on your experience with MBSE tools. Please take a moment to answer our survey questions to help us improve Innoslate. The survey link to share your experience with Innoslate will be shared in the chat shortly, and I will also include it in the email sent to your inbox this afternoon, along with the webinar slides and recording. Now, I would like to introduce you to our guest presenter, John Fitch, Principal Consultant and Course Presenter at Project Performance International. John brings over 4 decades of systems engineering, engineering management, consulting, and training experience to the PPI team. In 2012, John was certified by INCOSE as an expert systems engineering professional. Within the field of systems engineering, John's career has focused on decision management, requirements management, risk management, systems design and architecture, product and technology road mapping, and innovation. In addition to defense and aerospace, John has guided initiatives in domains such as communication systems, software, energy, nanotechnology, medical devices, manufacturing systems, knowledge management, and business process improvement. And now I'll hand over the controls to John and we'll get started.
Okay, thanks, Taylor. I appreciate the opportunity to share with you today. This is a subject basically near and dear to my heart. I've spent about 30 or 35 years actually focused on decision management and its implications. And so today I would like to share with you obviously some background and principles, key principles, big ideas in a sense that are the heart and soul of that approach. One of the things I discovered in doing this was, gee whiz, when you're doing projects, the decisions tend to follow patterns, and you can basically use those patterns to pre-plan, identify early on, and prioritize the key decisions that you basically have to make in a project, and then use that to focus your brain power on the most important stuff. A key aspect, of course, we're talking about here today is how do you capture these decisions within a model-based system engineering environment. So we look at the information model, the ontology or schema within the tool set to actually capture design decisions and everything else associated with traceability to and from them. And I'm going to do that using a couple of examples, basically a service design and basically also product design examples I've built over the last about a year or so, showing how basically I've extended the lifecycle modeling language and Innoslate as a tool to capture and support decision management. And along the way, I'll identify a number of what I'm going to consider usability gaps. The good news was that the lifecycle modeling language and the tool set are easy to extend, basically to add these classes of information to them. And so it's all now about usability and scalability. How do I scale up and capture large numbers of decisions efficiently and well? How do I visualize the data in a way that yields insight? How do I get people involved, basically engaged with making decisions effectively, and particularly managing change when things do change also. So I'll talk about usability gaps, and they all deal with just tool features and how I might want to visualize and navigate through decision information more effectively. And then talk about some next steps, some logical next steps after having laid a foundation here. What might we do with decision management on top of Innoslate? And so basically, my subtitle is Extending MBSE to Support Decision Patterns and Traceability. We're going to address obviously decisions that are really, it could be enterprise strategic. It could be very much detail oriented related to design of one particular product. It could be an entire product line, so how it's going to evolve over a decade or two, or a long-lived, let's say, defense platform that might be in play for 30, 40 years and go through multiple increments or iterations of enhancements and improvements. So we're going to look at decisions, and we can zoom in, zoom out, do this on any scale. The neat thing about this kind of approach is that it almost doesn't matter what the subject matter is. The fundamental thought process is consistent, and so is the information model with which you capture it. Bottom line in front of it, it's always useful to say what are my main points here. Kind of point number one: decisions are really the fundamental human thinking process that transforms a problem definition, what we typically call requirements or design goals, into a solution description, the design itself. MBSE tools today do a reasonable job of capturing the former, the requirements, and a good job of capturing the answer, the solution, but not the thinking in the middle. And so a large part of what I want to focus on is about how we uh, basically deal with that translation, how the problem gets translated into a solution through a set of choices. And so that failure to capture that decision in the middle or decisions in the middle has significant impact on the value we deliver to our stakeholders. And that's a shame, right? Because it's not that difficult to do. It's fairly simple, and the information model is kind of well understood. I've been doing this about 30 some years. I think I've actually done this on 11 different tools now. Some I've built, some I've extended, and I've been trying to promote this concept of kind of decision-centric system engineering for a long time with varying degrees of success. I've trained a few thousand people in various methods and things like that. So it hasn't been, a failure, but it's actually been a bit like pushing on a rope. What I've done here is I built two demonstration examples on top of Innoslate that illustrate, the language, the how you basically, capture decisions in a language like LML, and also basically in the tool set like Innoslate, and use that then to uncover, some perhaps gaps that need to be filled also. And the good news again is both the language as well as the tool set. I find it quite easy to do this work. A lot of promise. There's a really powerful decision management platform with very little effort, I think, to take the next step and fully support, I'll say, full life cycle decision management. And so I'm going to talk more about what we do to optimize now, as opposed can we actually make it work. Certainly, I can make it work today. It's a matter of working at scale, efficiency with new and large teams. Key idea is, of course, decision management is a lot more than decision analysis. If you just zero in on one decision that has popped up out of the ooze of a project, as if it's a surprise, right? And then you get try to wrap your head around it. How do I frame it? What's the question I'm trying to answer? Where do I go find the requirements and goals that from the stakeholders that drive it? And then basically then try to grind through that decision and come with a good answer and get it sold. You kind of already lost the battle. Because in reality, you could have proactively identified the most critical decisions up front, decided where to pour your resources and brain power into putting rigor and discipline and high confidence information behind those decisions, and made them basically successfully on time and right the first time, instead of having to rework them often. So the first step really is to understand what decisions need to be made, what questions demand an answer on my project, and what's the relative priority of those based on my experience in this domain I'm working in. And how do I basically, get that big picture understood so I can build what we typically call a trade study plan that says, let's understand the critical trade-offs we're going to have to make. And the good news, again, they follow pattern. So it's pretty easy to do this up front and get a good running start at it with, starting with a pattern. Most people do a reasonable job of making a decision when it's well framed and given to them. And so that's where most people focus. They focus on the decision analysis or make decision process. There's a lot of different techniques on how to do that and to do it at different levels of discipline and rigor. We need obviously a way to capture that data and make it visible, basically adjustable, communicatable to other folks so people can buy into a choice. But that's not really where I think most of the challenge has been throughout history. It's actually the ability to understand what needs to be decided. And then the other thing is understand the consequences every time you make a decision. Decisions basically create the future, and they really create all the other artifacts that are part of the MBSE world. They create new requirements every time you choose a solution to some part of your problem, right? You're creating hard edges, right? That other people have to interface with and interact with. So they create new requirements, new functional or decomposed when you pick a technology, let's say. They also create the physical architecture. The actual, basically they create the design, you want to call it that, and its packaging, its physical layout. And they also then create the tasks that need to be done in your implementation plan to actually realize the alternatives you're choosing. So we need to have decision requirement traceability, decision architecture traceability, and decision plan traceability if we want to understand how all this stuff actually works together as a whole. And that decision stuff in the middle is often missing in MBSE today. Another aspect, of course, is no decisions that we face today are never perhaps going to be revisited and perhaps modified based on new technology and new opportunities, or even changing requirements. So it's kind of useful to be able to manage decisions over time, to roadmap decisions. essentially a technology product platform roadmap is a set of decisions put to time that allows you to visualize how the choices you made in the past may be improved, enhanced, or threatened by other changes in the problem domain or the solution space over time. And then finally, the idea is to be able to manage decisions across domains, which is reuse decisions, revisit them across projects with basically look at different variants within a product line, apply them to different scenarios or situations, and basically get a jump start on a project by basically leveraging what you learned in the past. And so basically making decisions and have decision patterns that are ready for you to make you more efficient going forward. I'm going to cover basically this stuff very quickly, obviously in an hour today. And I've been writing quite a bit about this recently in the PPI Science News Journal. Here's some articles that came up, and these links will be available to you as well. I did a seminar a few years ago for the Incosi GFSE series on leveraging decision patterns. So there's a lot of additional detail out there, and some of the examples are basically what I wrote up in these previous articles. So more details are available, and even beyond these as well. Let's think about some of the big picture issues again. Lost decisions. We're not capturing decision information appropriately to the appropriate level of rigor and discipline. That has significant consequences. It makes it difficult for us to visualize the whole problem, which means we have important gaps in our thinking. Or we might have overlaps also where two people working on a common problem and not recognize they're doing so. So the ability to understand those fundamental questions and visualize them and understand who owns which one is quite important to get a big picture of where we're going to pour our brain power into produce a better solution. Obviously, you lose the fundamental thinking that is the rationale behind your design if you don't capture your decisions, and that is very perishable knowledge. Very important knowledge, but very perishable. You can lose it because of turnover. You can lose it just because of human memory. I'm 70 years old now, right? And guess what? My memory's not as good as it used to be. And so you're going to forget the rationale if you don't capture it to appropriate level of discipline and rigor. You also basically lose the connection with all the other data that basically drives the ability to make high confidence, design decisions. If you don't have the traceability associated with these decisions, when things change, and they will change, either in the problem domain, your requirements will change, your stakeholder goals will change, or the technology in the solution space will change as well. And it's inefficient then to revisit choices and understanding what the ripple effect is of a change if you don't have good decision traceability. It helps you basically, if you don't have it, it's really difficult to do large scale revisiting of a design when there's some breakage of it because of that kind of change, and do multiple decision optimization and trade-offs across the life cycle. And of course, you've lost the derivation traceability thread that produces the next level of requirements as you've done that as well. And basically, you're not being able to take advantage then of obviously what you learned very efficiently in making other projects go faster and produce better results. And that all leads to basically lost time, lost value, and lost customers. Some first principles here. I use a bit abnormal definition of decision, and it served me quite well. In my world, it's part of the problem domain. It's a fundamental question or issue that demands an answer or a solution. It's not the alternative you choose. And that separation between the problem, basically seeing the decision as a question or a problem, and the alternatives as the solutions is really important to allow you to use decision patterns, because the problem pattern is very stable across a situation type, where the solution space changes much more rapidly because of technology evolution. And so it's a key idea here is to separate and treat the decision as a question that demands an answer. Design is fundamentally a decision-making process, a big idea there. Obviously, the system design may be the result of 50, 75, 100 decisions, not all of equal importance, of course. If you do have, the patterns, though, you can actually use those patterns to jumpstart any project. If you basically have an explicit decision model of your project, it needs to be proactive about understanding the important questions, efficient in tackling them, and effective basically in making those choices, getting the right people involved, the right kind of data. If you don't have it, you treat it as an ad hoc process, kind of happens to the side of all the other stuff we're doing, like drawing up models, let's say, you get the opposite results. It's inefficient and less effective. Other big idea, and again, it's kind of fundamental. Decisions are the source of all requirements. all requirements to drive requirements. They come from an upstream decision someplace. I've challenged people for decades to find an exception to that. I've never had somebody able to do that. I can always trace a requirement to an upstream decision somewhere, and basically you can just take that to the bank. That's always going to be true. And yet our system engineering traceability models don't recognize that very effectively. And of course, decision traceability demands capture of decision rationale of the why, and also the consequences. And that's kind of a rich data model. It's not just a few words in a text blob inside of a architectural, entity within a database. So there's big principles there. Let's go into decision patterns, right? I'm going to show you some decision patterns. I can't dive into in detail in this session. Just give you a sense that says they're comprehensive. They cover enterprise strategy. They covered typical system and product design. They cover design of services. I even use them for designing courseware, courses I deliver. So here's the top level enterprise strategy pattern. Each of these blue boxes is a decision question. What's the vision of my organization? Let's say, what's my brand identity? What core competency strategy do I have? How am I going to grow certain process core competencies, technology core competencies? Well, how am I going to play in the value chain and make money and be successful? How am I going to differentiate myself in the value chain? Basically, what are my target markets and market positioning? How am I going to win, market share by having a superior product or service portfolio? How I price my products and my overall platform to deliver my capabilities to them. What's my infrastructure that basically I build my company on, as well as who owns what and what happens to it at the end of life, perhaps. And so basically, this gives you the business context for most of what we historically do in system engineering. And you'll notice that there's a bunch of different patterns. The process capability pattern we'll look at in a second basically helps you, effectively design process capabilities. The system and product design pattern can be used for the product portfolio decisions on designing products and systems, as well as can the platform strategy can be used basically using that same model. And service design can be basically used to then populate out the service portfolio. So these patterns fit together. The business context is kind of the top level. You can use this to start a new company of any size or scale, and then find the lower level patterns to dive a bit deeper. Let me dive a little deeper now into this approach. Here's the product system design pattern, overall top level solution concept. In what situations or use cases will this product be employed or system be employed? What kind of value proposition will it offer in each of those use cases? What kind of use case flow or operational sequence is going to be what's the basis of that? And what role will the system play in that operational concept for each use case? That typically is how we're going to package value as features, and then the overall feature concept for each key feature, what operating regime we operate in, and that kind of gets down to the fundamental science we're going to use. Are we going to, conquer the world with nanoscale, quantum behaviors? Or we're going to do it with bulk physics, or basically high energy plasmas? Basically, what science will I employ to help me solve my problem? That could also be, human behavioral science as well, if we're talking about human driven systems. Then you get into the architecture branch, where you have basically the state model, the functional model, and a bunch of the other aspects, the hardware, software, architectures, platforms, and obviously a whole lot of interfaces there as well. External interfaces basically being the overall context that your system operates in, and the system lifecycle. These are all, again, fundamental questions. Basically every system you ever design, you make these choices. The only question is, do you make them visible, explicit, and capture them with an appropriate level of rigor? I will note there's different types of decisions, right? And you'll notice a couple of different bits of notation here in this simple diagram here. If I have a decision that has more than one answer, I'm going to perhaps service more than one use case in my product. It's going to fan out, and this entire branch is going to get repeated for each alternative I commit to the next level up. Same thing for feature set and for external interfaces and lifecycle phases. And so there's places where the model basically leads to another instantiation layer, kind of a rolling wave concept of building out the decision model. You don't build the entire decision model up front. Sometimes you have to make a choice in order to identify the next level sets of branches. Now, the good news, again, that this whole model is language and tool independent. And the other thing I'll note here is that you probably intuitively know this, right? This idea of a decision breakdown structure as a tree doesn't last, when you get very deep into the model, because as you make decisions, there's cross connections between them. The drive requirements in this decision will affect, will drive the constraints or criteria in other choices as well. That those cross connections, though, are somewhat unruly, and they are all based on the answer you choose, the alternative you pick. They're not based on any fundamental logic of the decision pattern itself. So this is where the decision model becomes a decision network over time. It initially starts as a thinking breakdown structure, decision breakdown structure. It eventually gets wired together depending on the answers you choose. And that's why system engineering is hard, because these decisions all can interact in unexpected ways based on the answer you pick. And that's where the real system engineering skill comes in, is understanding how those connections actually do work, and how the house of cards won't collapse when you perhaps change one thing in it. Process capability patterns, again, a simpler one here. I'm just showing again, typically the way a decision is expressed. And this shows the three different types of choices: the single answer technology decisions, the multiple answer portfolio decisions, and the ones where the answer is an architectural model, either functional or physical architectural model, where basically the boxes and arrows lead to the next level of choices. You typically have a design decision for each box and for each arrow, let's say for each interface as well. This is basically what I use when I was trying to design a better process for doing system engineering. Service design, if I'm again, I'm a consultant for 30, 40 years here, right? I've designed many consulting engagement type services, and I use this kind of pattern to help me do that. Very similar, it's based on the product design pattern, just scaled for human intensive, kind of knowledge driven services. The foundation, of course, for doing all this and capturing it is going to be some kind of information modeling, right? Understanding what classes of data should I be capturing in order to capture decisions effectively. And what I've shown here is kind of a high level ontology of that. As I said, I've done this about 11 times now in my career, thinking about how to capture decision information. And the four core elements are the design decision question itself, the criteria, right, that represents how I define success in the context of any one decision question, the alternatives, right, which are possible solutions to the decision question, and how well the alternatives perform against each criterion, which are the cells in a typical evaluation matrix. That's where you gather data and do estimates of this is going to give me this kind of range, this kind of cost, this kind of mobility or lethality, depending on what kind of system I'm talking about. And those are all estimates, or they're perhaps derived from simulations or models. This is where a lot of money gets spent in coming with numbers that express the value or effectiveness of the various alternatives. Of course, the decision is also influenced by what could go wrong with the alternatives, how they could fail across their life cycle. We call those risk or failure modes. Also, what could go better than expected, like a windfall. This could lead to new business opportunities if we go down this particular path with it as well. The alternatives are typically comprised of physical solutions, assets, components to make them up, and the alternatives you pick then produce new requirements. The performance basically is some form of a measure, right, which may be built up through a set of equations. And of course, criteria come from upstream requirements and design goals that came from higher level decisions. What I've shown here is just basically my initial mapping I did a while back, right, on how would I map that to the lifecycle modeling language, LML, right, and its classes, the action class, the requirement class, the characteristic class, the asset class are the basis of essentially the parent classes for each of these. These are all subclasses. So that was the good news. I didn't have to actually create any new core base classes in LML. I was able to extend what was there and leverage what was already been built, which I think indicates in the quality of that language as well. There's obviously additional trade-offs to be done. I'm not going to say my prototype of this is ideal, optimized yet. I'd like to engage the LMO modeling organization in more detail to think about some trade-offs associated with that, and also to produce perhaps even a more elegant model over time. And obviously then talk about how to implement those in more detail in Innoslate. If you take the two things I've just shown you, the decision pattern, the decomposition structure of the problem space, and the information model, you end up with this two-dimensional view, which allows you to take a lot of information and stick it into a structure and have a place for everything and everything in its place. That's a kind of amazing thing, right? I've had the privilege of doing this at least 150 times with different project teams. And it's kind of second nature once you learn how to do it, but you'd have to internalize the decision pattern and take ownership of it. And you need to essentially have a good set of inference skills and then recognize, well, what's a requirement sounding thing? What's a criteria sounding thing? What's a decision question sounding thing? It wasn't alternatives on anything. When you read it, let's say a source document or talk to stakeholders. So all these different classes of information, kind of a different smell when you actually detect them in some source data, and you do kind of a mapping process. This, by the way, I think is something that could be powered by AI in the future, with at least to accelerate the process of doing so, and be less dependent on old guys like me who have just done it through a lot of experience. So, but this is a fundamental idea here that there's essentially a way to take legacy data and very quickly understand what choices have been made and how all of this data fits together into a more comprehensive approach. And this is really the methods engine that powers this decision-driven approach to system engineering and design. The actual schema that I recommend, right, for building this out on top of Innoslate, I first started doing it with version 4.9, and of course it's been extended since then. It looks a bit like this, right? I subclass the action class to create the design decision and add some attributes to it. I took the requirement class and subclassed it into a criterion, what the requirement or goal means in the context of this particular design question or decision. The alternative class was a subset or a subclass of asset with quite a few additional attributes captured on it. The performance class was a subclass of measure, which is a subclass characteristic. We already had risk, and I basically extended some attributes on top of that, and then potentially produced an opportunity subclass from it as well. So the good news again was the information architecture was pretty straightforward to extend and easy to build on top of Innoslate. And I've got a place for everything now. Again, I'm not sure it's optimum, and there's some questions I have about reuse of particularly the relationships. Should I reuse relationships between subclasses, or should I leverage the higher level parent class relationships, and how that gives me different visibility and information. So work to be done there to be optimize, I think, the results. But the good news again, there's a place for everything in this kind of model, and it's quite a mature model, been used quite a few times. We always have this kind of problem, right? We never start really the top end of anything, where we're the one conceiving, something from scratch that the universe has never even thought of, perhaps. We're almost always jumping in where somebody's done some decision making above us, and we're asked to come in and take over that decision making. So it's kind of important to understand this, what I call the decision frontier. What choices have been made already that are the source of my requirements and design goals, essentially my baseline, my problem baseline. And again, if you understand these decision patterns, you can quickly reverse engineer, right? The decisions have been made by doing that mapping exercise I just showed you. You can then look at it and say, let me just meet with the stakeholders and say, I think this is what you've already decided. I'm showing now these grade decisions on the left-hand side is always already being decided by people higher pay grade than myself, stakeholders. They're product scoping type decisions typically is what they are. I could use that to validate the requirements I've been given versus the decisions they claim to have already been made, and look for gaps and mismatches. And often when you do this with stakeholders, you find, what, they argue among themselves. Did we actually decide that already? And they discover, well, maybe we haven't really thought through all of our use cases yet. And maybe we haven't figured out how to package value into features very well. And maybe our idea of a hardware platform needs to be revisited. Maybe we can't reuse this thing we thought we were going to build on top of in the past. So it's a very interesting exercise that you uncover a lot of fuzziness in people's thinking up to this point, and it gives you a chance to nail it down before you commit to doing the work on the right-hand side of this diagram. Your design responsibility, let's say, as a contractor or development team. But basically, then you get on the right-hand side, you can say, let's use the decision pattern as a proactive decision making and analysis plan, so we can prioritize, assign ownership, figure out where we're going to use simulation modeling, prototyping to actually inform choices instead of just expert opinion, assign budgets to this kind of each of these choices in order to make progress. So again, that's a decision-making plan. And with this, you basically can have, two fundamental ideas: validate requirements from closed decisions, or accelerate the design process going forward. Both quite important, right? Poor requirements lead to poor outcomes, and basically ad hoc decision-making is inefficient. It doesn't optimize parallelism and efficient, one pass through effective decision-making. So the patterns have a lot of power there, but it does require the ability to use them and a way to capture them and instantiate them to be successful. Two examples I'm going to share very quickly here, right? basically one was designed of our project Jumpstart service, right? PPI does it, offers this service where we basically gather information from stakeholders. We set up a decision repository. We basically do the magic of getting that data imported into a database of some sort. We do that decision and information mapping. We produce essentially a model, share with stakeholders, do what we call a decision blitz, and we basically confirm closed decisions and perhaps use that to validate requirements and resolve requirement issues, and sometimes both, and basically identify open decisions, prioritize and plan the decision analysis of trade studies, and then use that to make sure that the scope of what has to be decided fits within the project scope, and then obviously facilitate choices and maintain this across the life cycle of the project. So that's kind of a service we offer. Second example is one that is kind of interesting. There's a fellow that's a distant relative of mine, also named John Fitch. He was a fighter pilot in World War II. He's also the great great grandson of the John Fitch who invented the first steamboat back in the 1780s. Well, this guy developed a need for speed as a fighter pilot, and he became a Formula One race car driver after World War II. And in 1955, he was in the racing in the Formula One race, the 24-hour race at Le Mans, France. Right before he took the wheel from his partner, Pierre Levey basically lost control of his vehicle, killed himself and about 80 spectators. So this John Fitch basically devoted the rest of his career actually to highway and racing safety, innovations. He has 15 patents, and one of them is a highway energy absorbing deceleration barrier, a highway sand barrel array that basically reduces the deceleration forces on the occupants of a vehicle that loses control. So I use those basically two examples, the service design as well as the design of this product from the patent information as an example, and build out Innoslate instances of these two problem situations. In the case of the service design, here's an example of a decision blitz result dumped back out to Excel. Here's the decision question here, and here's the answer of how do we design that service. This is a small slice to a much larger model. There's about 40 decisions, I think, in this particular model, if I recall. The alternatives, essentially a kind of a one-page summary or two-page summary of the fundamental questions and the answers. I could also capture the rationale, why behind it. And so a good compact way to communicate decision thinking and rationale. Here's the crash barrier decision breakdown structure. About 25 decisions I was able to reverse engineer from the patent itself. What I found, of course, in doing that, and I'm going to talk about some of the usability gaps here, was the effort to instantiate cross-project decisions, to have a decision model in a project, a pattern in a project, then instantiate it kind of one at a time was a bit inefficient. I was looking for some leverage to actually allow me to instantiate large branches of the model quickly, but still selectively. So I think there's some usability issues in terms of doing that effectively well. And then also how to visualize most effectively kind of where you use traceability. If I have a decision pattern in a project, how do I visualize where it's been used in other projects, and then use the feedback loop to say, what did I learn from each instance or each use to improve the pattern? So I think some where use traceability could be improved also. Again, decision summary table is another example of what you can capture there. This for the crash barrier. This is, again, a variance of this report with additional columns added can be used to conduct a decision blitz with stakeholders and get consensus on decisions that have been made, discuss decision priorities going forward, to assign resources and responsibility, build analysis plans, and the like. I'd really like to have a way to visualize, my evolution, my thinking, my design, not just in a table, but also graphically. And so I'd really like to see a kind of a two-panel, multi-panel box approach here, where I get a decision question at the top, the answer I've chosen, or even those I've considered in the lower panel of the box, and then be able to see that represented as a hierarchy. So one kind of one-page design summary that basically I've used here historically in the past, and today I can't quite produce that as efficiently as I'd like. So that's a request to basically for the Innoslate development team is to give me a configurable box so I can stick different content within different panels within the box and then arrange that information in a hierarchy. I took a stab at that, right? I used the spider diagram. I was able by basically using the decision as one type box, the alternative is another box, to essentially replicate the idea of a two-panel box by putting them adjacent to each other, then showing the decomposition basically a process here. But that was a bit busy. It took a little bit more effort than I'd like to have. I'd like to have the built-in capability to do so. Another question that came up when doing this is I overloaded the use of the decomposition relationship. I used the decomposition between decisions at higher level to lower levels, right, is a decomposed by relationship. And the existing relationship, basically how a asset can be decomposed to lower level assets, or alternatives can be decomposed into that, I leveraged also. So I'm overloading the decomposition relationship, and that may not be the best, most optimal approach as I've thought about that. And the other aspect, of course, here is I've got a whole branch of this model is basically a set of technology choices. What technology or method will I use to deliver function X and decelerating the vehicle or controlling deceleration? It'd be useful to have a traceability relationship there between the system functions, the functional model, and the decisions that design the answer to each of those functions. That way you can make sure you have a decision for each function and vice versa. So the functional scope of your system has been captured effectively in good trait studies or decision analyses. If I dive into the make decision process now, right, here's a simple example, right, of the kind of data that goes in a typical evaluation matrix. Typically have like criteria rows, you have alternatives columns that can be inverted as well. You've got the performance information of how effective the alternatives are against the criteria, right? Those are cells. There's multiple attributes of information or properties. There's the estimates of performance, uncertainty about that. There's a go, no go judgment. There's scores and weighted scores come from that. And so that's a pretty compound, rich set of data that typically is represented as cells in a matrix, depending on the format you use. You also typically would have for the alternatives, you have the various risk and opportunities that tend to be the tiebreakers. Another way to handle uncertainty, right? Particularly special cause type uncertainties. If this thing occurs, then the following bad things happen, and kind of all bets are off on the rest of your estimates here. And so this is the data that typically goes into informing a good decision, right? And it's very compound, rich data. I can capture it today in Innoslate, right, pretty effectively in the language, but I can't visualize the matrix as efficient as I'd like to. So I can inform the decision analysis process, but not with the insight I'd like to be able to do as well. I can capture again the matrix in the database view or an Excel export of that. I use that Excel export probably to drive, an Excel-driven, evaluation matrix, and that's probably the workaround I would emphasize today. But basically, I can't visualize it as well as I'd like, and it's inefficient to build the model one object at a time. So I think having a matrix input view and a way to perhaps suck in spreadsheets also would be useful in terms of populating the entities that populate a typical decision analysis evaluation matrix. I also don't have the built-in scoring calculations that typically would be part of an evaluation matrix. Certainly can be done with an equation. I just haven't basically built that out yet. And here's what the information model looks like. You can see it's a bit of a maze here. Basically, I have to create the decision, the alternative, the performance estimates, the inverse of the criteria, and link them all together. So I'd like to have that happen behind the scenes as much as possible, by understanding the information model. There is the ability to capture, radar diagrams, which are quite effective at communicating performance and also risk and risk matrix. So I have that kind of visualizations available. What I can do, if I look at the next example, I can't very effectively show multiple alternatives on top of the same radar or spider chart here. And so I'd like to have more ease, again, having this be a kind of an automated view that I basically just click on, select these two alternatives or three alternatives in this particular decision, have the criteria pop up. I can rearrange them perhaps based on weight and have me the ability then to compare and overlay different alternatives on top of one matrix. If I go now to the final step, which is kind of managing decision consequences, right? The challenge we have here, right, is there's a real complexity associated with how decisions basically translate the problem into a solution. You've got requirements, some of which apply and don't apply to a particular decision question. And the requirements as written typically don't apply one-to-one as worded as effective criteria. So you have to do some kind of translation. What does that requirement or design goal mean in the context of my particular decision? Those are criteria. And then that basically leads to, those constrain the decision question, right? Those are how you define success. That decision question then allows me to choose between alternatives or reject other alternatives, basically analyze the rest. And of course, that's where the evaluation matrix data comes in, has alternatives perform against the criteria. That's this data here. Alternatives will have ways they can fail, risk, which can be mitigated, and opportunities which can be grown by various actions. If we decide to mitigate a risk and grow an opportunity, those can become optional requirements. It's not mandatory we do that, but we improve our probability of success. We typically would do that. And of course, the other thing, of course, that happens is when I pick an alternative, it has inherent consequences. They're part of its definition, its structure, its behavior, its footprint, its interfaces, and life cycle. And that's really where drive requirements come from, without exception. And we don't capture that decision in the middle trace. Kind of these middle 5 columns here, right, are typically missing. We try to trace from here all the way over to there without the information in the middle that explains why this requirement drove this decision or didn't to pick this alternative that led to this rather strange consequence. And that's where the maze of how decisions interact with each other is created, essentially one decision at a time. It's created through the alternatives chosen. That's the reason you can't basically go right from requirement to the next level requirement without missing a lot of important information. It could be that, again, a 2x change in this requirement might not change the answer at all, but a 5% change in this one might cause this alternative to fail, and this one to become better, and a third alternative be necessary, which leads to new consequences that flow down through the rest of the choices in your overall system lifecycle. So this is the real complexity we like to be able to manage. And we can do that pretty effectively. I captured for the Christ barrier. Here's the alternative fundamental physical architecture is a configurable array, uses a similar shape, varying in size and sand fill. And here's the kind of requirements that were derived from that particular alternative. The challenge we have with that, though, is how to visualize that traceability, because that is essentially a many to one to many visualization topology. And while I could do that with a spider chart with a fair amount of manual effort, I really like to have that become more of a built-in visualization. So some way to show a typical tree structure going both directions, upstream and downstream, based on understanding relationships would be a very useful visualization. I can do it in table form, right? But that's sometimes not the best way to get the idea across. So some way to visualize this end-to-one to end topology of traceability would, I think, again, be quite useful, because it fundamentally is how things happen. You don't have basically, it doesn't just flow from left to right. One requirement becomes many. It flows through a decision model where an answer you pick is the source of the next level requirements. Obviously, you want to be able to support decision architecture traceability. It's decisions that create each of these elements in a system breakdown structure or product breakdown structure, as well as the interfaces between them and how those interfaces are going to be implemented. So it's quite important to understand that. And basically, how can I visualize that decision to architecture trace, and particularly where multiple decisions may affect the same architecture element or the same interface. It's not just one choice that sometimes affects a interface. There's typically a many relationship between decisions and physical architecture. Similar goes for functional architecture. There's always this issue of trying to align, make choices. How am I going to implement this set of functions through various technology we're going to pick? That leads into a logical architecture based on the next level of decomposition of those functions based on the technology chosen. Physical architecture implements that. You have to iterate between those two and keep them aligned. And the physical architecture basically is elaborated through these lower level choices. So there's a bit of a challenge, it's kind of a three-legged stool almost. You got the logical view of the system, the physical view of the system, and the decisions that actually kind of sit and tie those things together. And I'm not sure the best way to visualize that, and I think some good experimentation can be done there to improve those visualizations. Okay, kind of in summary, right? Um, uh, again, good news is the LML and Innoslate, I think, a great foundation for capturing the full range of decision management information. Areas of improvement, right? We need ways to more efficiently instantiate a decision pattern to give you a whole project visibility up front. We need perhaps better ways to efficiently capture and visualize decision logic. That idea of requirement many to one to many traceability is, I think, a useful improvement. And I didn't talk much about it here, but we can capture time, in your tool set and language. It's very useful to be able to visualize that as Gantt charts, basically show how evolutions of alternatives and performance of those alternatives may change over time. Essentially, build a roadmap looking visualization basically through that approach. And then obviously the ability to instantiate patterns, harvest lessons learned from them, and then have where use traceability to help you then maintain that entire model for additional use. Next steps. Intent is to work with the Lifecycle Modeling organization on language trade-offs and produce a decision management appendix for the standard. I like to work with obviously the Innoslate team, right? Look at near-term decision management features, low-hanging fruit, things that may be just done by tweaking something you've got already, not creating new visualization, but tweaking it a little bit and how it can be visualized. And also basically ways to improve usability and kind of in the small. And longer term, right, I'd like to look at ways to enable some decision management capabilities through AI. You've got a good AI engine already built in. I'd like to be able to extend that and improve it. In parallel with the work I did here, right, the Encoding Decision Analysis Working Group has come up with a decision analysis data model. It's got some gaps in it from my perspective, right? And it doesn't have a lot on pattern instantiation and big picture decision patterns. It doesn't have much on decision everything traceability and multiple decision trade-offs, and it doesn't have anything on road mapping that I saw anyway as well. So there's a potential engagement there with that organization, as well as with SysML folks, right? And basically the OMG, and trying to align these different models and make them all effective in capturing decision data. With that, I think it's actually time for some questions.
Thanks, John. If you haven't done so, please send your question to the panel on the right that pops up after clicking Q&A on the top bar. Please help us improve by filling out our Innoslate experience and feedback survey. You can find the link in the chat in the email coming to you this afternoon. If you're interested in having our team help you make better decisions with Innoslate, contact our sales team. You can reach our team by email at sales@innoslate.com or through our website, specinnovations.com/contact-us. All right, we've received several questions already. We'll answer as many as we can before our time is up. First question is, if we are novices to formal decision management, what are some small steps and shortcuts that we can take to begin and make progress in this discipline?
Mhm. Yeah, what I think I learned over the years, right, is even though there may be 75 to 100 decisions in the design of a typical product, you can make a lot of mileage if you just have like a top 5 or top 10 decisions list initially. Don't worry about the deep, rich structure as well. But basically, you just have a discussion on what are the big questions that are going to drive success or failure of a project if we get these wrong, and then use that kind of a Pareto approach to say which of these decisions have the biggest impact on success, how we're going to allocate our brain power and analysis resources and rigor to those, and then capture decision information appropriately based on that. So use a Pareto approach to always drive rigor and discipline to match importance.
How do we incorporate capabilities and scalability into this approach/model, knowing that decisions and capabilities are not synonymous?
Obviously capability it can be represented by a model, right? And those models typically be represented functionally and then implemented physically, right? And so I do think this model covers all that. The decision patterns, I have to go back about 30 slides to get to it. But if you look at the decision patterns in terms of functional view here, right? Oops, that's enterprise. Just take this one here, right? You've got a functional and physical view. You can represent any capability, right, as a functional model and physical model, and you can, as a result, use this particular. What's the method to deliver this capability or this particular sub capability can be used this particular branch of the model, and the physical implementation of that can be in hardware and software, or human operations, right, as well. So I do think it scales quite well to that. That's just another level of the same fundamental thought process and architecture.
Question, how much progress can we make on decision management within Innoslate while the usability gaps that you've identified are being resolved? What are some interim workarounds?
Yeah. Yeah, so I do think that, we have a place to capture all the data quite efficiently and well. I think the simplest short-term approach would be if you want to capture good evaluation matrices, those can typically be represented in Excel, and we can get the data out of Innoslate quite efficiently into Excel. And there's got to be a little bit of mapping to take the dump from Excel from Innoslate and have it drive the evaluation matrix visualization. It'll take a little bit of work in Excel to actually make that happen semi automatically, I think, right? But certainly it's doable, right? The data's there, just a matter of getting it pulled out. I think the bigger question is how can we take an evaluation matrix that exists today in a typical format and import it and have it produce the appropriate data inside of Innoslate. That's a bit of a work to be done. That may take a smarter importer. But other than that, I think getting some of the data just back out to Excel and visualizing the decision analysis data in that format is probably not a bad inner workaround.
Next question, what might be some key features of an AI assistant for decision management?
I think that kind of falls in two aspects, right? One is this is a bit of a rolling wave model, right? So again, is there some decisions in the pattern you can't instantiate until you made the decision above? I can't come up with the value proposition for use case until I've decided to follow or pursue that use case or support it in my system. If I've thought about 10 use cases and I decide to implement 5 of them in my first release, I'm going to have to understand the value proposition and use case flow for each one. So there's an instantiation process that's a bit difficult to manage. So if we could have AI kind of guide us through the process of, okay, you've just made this choice, and this leads to the next level set of questions. It could be essentially be a bit of avatar almost to help us with that process, perhaps. Second would be, I think, again, low-hanging fruit would be just instantiation of the pattern based on existing data, right? And if again, I went to that kind of this two axis model here, it just takes some language skills to read something and say, oh, that's a feature type decision, that's a use case flow decision, that's a research strategy choice, that's a solution concept decision. Oh, that's a criterion, that's an alternative, that's a performance estimate, that's a risk. And that's something should be LLM should be pretty effective at sniffing out, I believe, once we train it with an appropriate quantity of data with enough diversity. And so I do think there's a real capability there that's really powerful long term that can make the ability to jumpstart a project much quicker and less costly than it even is today.
Thanks. That looks like all the questions we have for today. John, could you please go to the next webinar slide?
Okay, and that's the end.
We would like to thank you again for joining us today. As a reminder, we will be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for next month's webinar, Cybersecurity and Systems Engineering, Protecting Your Digital Projects, with Dr. Stephen Dam on Tuesday, October 21st. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. Next slide. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day. We hope to see you at our next webinar.